function that just takes, say, three numbers, a, b, and c, and returns their sum, well, you're only ever using a handful of variables.
A spot for A, a spot for B, for C, and maybe one for the result.
Right. 4 or 5 memory slots. That number is fixed. It doesn't matter if those numbers are huge or tiny. The number of slots is always the same. That's O1.
Now, here's the part that I think trips up almost every beginner. Let's look at a function that takes a massive input, something that calculates the sum of every single element in an array of numbers.
Okay.
That array, that input n, it could have 1 billion records.
It could.
And yet, the source material insists that this sum function is also O1. How?
How is that possible? If the input is 1 billion numbers, isn't that a huge memory drain?
That is the essential question. And it brings us right back to that rule about auxiliary space.
The extra space.
The extra space.
Yeah.
So let's imagine you're summing up every transaction at a bank. N is huge.
Right.
But look inside the function. What does it actually create to do the job? Well, a variable for the running total. Maybe one to keep track of the index.
Exactly. You've got a variable for total, one for I, which is the index, and maybe one for the array size n. That's it.
It's like having a small scratch pad.
Precisely. A tiny fixed size scratch pad. You're using it to keep a running tally, but you are never, ever creating a new array that's also 1 billion elements long.
So you're just reading the existing data.
You're just reading it. The source material is very clear. The input array is passed in, and it is not counted as part of the auxiliary space.
So that input memory is...
Yeah.
It's a cost we were going to pay anyway just to hold the data. We're only measuring the additional cost to the algorithm.
That's the aha moment. Since you're not creating any new large memory blocks, the function operates with a tiny constant amount of extra memory.
Regardless of n.
Regardless of n. That's why an algorithm can process petabytes of data, and you can still, with a straight face, call its space complexity O1.
That's a huge takeaway. If you see a process that just iterates and tallies, you can instantly flag that as being very memory friendly.
Absolutely.
Okay, let's transition. We've seen how to avoid creating new space. But what happens when you have to build a new structure whose size depends on n?
Well, then you move out of that constant realm.
And into the world of linear space, ON.
Right. We hit linear complexity the moment we dynamically allocate memory that mirrors the input size. If you double the input, you double the extra memory you need.
And the sources show this with a copy array function.
Yep, a simple function. It takes an array and its size, n, and its only job is to return a completely new, identical copy of that array.
But why would you need to do that? Why not just use the original?
Well, sometimes you need to modify the data for one step, but you need to preserve the original pristine version for another step.
Okay, that makes sense.
Or maybe the original data is stored somewhere that's slow to access, so you pull it into a faster local working copy.
So how does the memory get allocated here?
You have to explicitly ask the operating system for a brand new chunk of memory, a chunk that's exactly n elements large.
And because the size of that new chunk is directly tied to n.
The relationship is linear. If n is 100, you need 100 slots. If n is 1,000,000, you need 1,000,000 slots. That's the definition of ON space complexity. The auxiliary space grows proportionally with the input.
So it's the difference between, say, tallying a checklist in your head, which is O1, and deciding you need to make a full photocopy of every document in a filing cabinet. That's O1N.
That's a perfect analogy. The stack of paper you create is directly proportional to the stack you started with.
And that highlights the trade-off.
Oh.
ON is.
Yeah.
It's usually fine, right? It's predictable.
It's perfectly acceptable for most applications. You know, if your system can handle an input of size X, you know exactly how much memory you need to set aside. You're just trading memory for convenience.
Right. It's a reasonable, predictable cost.
Exactly.
But let's move past proportional scaling into, well, the danger zone.
Quadratic complexity.
This is where memory usage can get explosive.
Yeah.
What kind of process requires memory to grow with the square of n? This is ON squared territory.
We hit ON squared when the extra space we need scales with the square of the input dimension. It's almost always because every element in the input needs to interact with every other element.
You mean like comparing everything to everything else?
Precisely. If n is the number of items and you're building a structure to represent all possible pairs of those items, the total number of pairs is n times n.
That sounds like you're building a giant grid or a matrix.
And that's exactly the example from the source material, a function that creates a data structure like a matrix, where both its height and its width are defined by that input dimension n.
So if you're mapping, say, the travel time between every city in a network of n cities?
You need n rows and n columns.
Okay.
If you have 10 cities, you need a 10 by 10 table. That's 100 spaces. But if you expand to just 1,000 cities,
1,000 times 1,000.
1,000,000.
1,000,000 spaces.
Wow, okay, so the input size only went up by a factor of 100, but the memory cost went up by a factor of 10,000.
Yeah.
That nonlinear growth is terrifying. It is. That dependence dictates the O(n)² space complexity.